I will not today be talking about AMD GPU, taking a little break from my regular schedule to talk about Dagger.jl. This is the other part of my work here at MIT's Julia Lab. What is Dagger? So Dagger from a high level is a Julia library really focused on parallel computing, and not just one form of parallel computing. So I'm talking about multi-threading, I'm talking about distributed computing, I'm talking about GPU programming, I'm talking about parallel storage I/O and things like that. Really, whatever hardware you have, Dagger wants to target that and make it easy for you to use that hardware effectively from Julia. I picked up Dagger.jl maintainership a few years back. It was originally developed by JuliaHub, previously Julia Computing, and ever since I picked it up, I've really been focused on the ability to really be able to write code once and run it at any scale. So I've got a laptop, I want to be able to write code on my laptop where it's convenient and easily just push it to a supercomputer or a cluster or whatever, and let it make use of whatever hardware is there most effectively without having to go and change a bunch of code and learn a bunch of different things. So there are some problems in our ecosystem, and maybe I'll hide the Dagger solutions. So there's some problems in our ecosystems that Dagger does solve. For example, if you've ever tried to use distributed computing for a problem, and then you're like, I want to add multi-threading, and then you want to add GPU support, or even some portion of that, you find that it's kind of hard to actually do that effectively. To say, I have a bunch of work and I want to run it across all of these modalities. It's difficult to do that because our libraries weren't built for that in the first place. And so they don't exactly compose. Kind of a corollary to this is that, or really one of the immediate results of this is that you can't spawn a task with some work and have it run anywhere, not with built-in Julia standard libraries. You can't just say, here's a task that's going to do some work, and I don't care if it's going to run on a local thread or a thread somewhere else on another worker in my cluster. You can't really do that with the built-in Julia tools available. There's also this problem that, as we've seen from Tim's talk, that we have more and more hardware that is available of different kinds from different vendors, which kind of all follow the same idea, but they're all different implementations. They all have their own drivers, they all have their own compilers, and we also have different interfaces that we want to work with. Some people want to work with tables, some people want to work with arrays, some people want to just do stuff directly with tasks, kernels, etc., etc. And so we have this problem of mapping all of these abstractions to all of these backends through a unified system, which gives you still all of the same features that you want. And of course, users have all sorts of crazy configurations, and we want to try to support all of them. It shouldn't matter, whatever hardware the user has, we want to try to support that as best as possible. Often users don't really have a choice in that. So Dagger's solution to all of these problems, multiple pieces. So for one thing, Dagger has a unified task concept. So Dagger.atSpawn constructs a task, and I'll show some code in a little bit, but basically it has a unified task that can run anywhere. It can run on the worker that launched that task. It can run on another worker, and it will pick a thread. It'll pick whatever Julia thread is available, and it has a built-in scheduler that kind of decides, hey, I have all this work. Let me just kind of throw it out all over the cluster and just utilize our resources really efficiently. Don't mind the machine learning part of the heterogeneous scheduler. That's kind of just a thing that's still work in progress, but we do some reasonably smart things with scheduling. We don't, send a bunch of data around, wasting a bunch of time transferring data for no good reason. That's really what that means. So we also have high-level APIs for, as I said, tables, arrays, stuff like that. They all use the same underlying support from Dagger. There's no special thing for tables or special thing for arrays. It's all the same low-level API that Dagger exposes to these abstractions, and it all just works fine. And because you have the right primitives that you need to really build all of these abstractions. So we also have hardware awareness. So you load Dagger, and then you load CUDA.jl or OneAPI.jl or what have you, and Dagger detects that, oh, now there's GPUs. Okay, I'll be able to use these, no problem. You don't have to do a lot of work for that. So let's take a look at one of the main interfaces that probably the people here are familiar with, which is distributed arrays. So Dagger has a built-in distributed array implementation called the D-array, and it kind of works like you'd expect. In Julia, this is how you can allocate a random array, 64 by 64, and in Dagger, you can call distribute with that array to split it into blocks of 16 by 16. So we'll take this array that's, you already have allocated, and you can split into partitions, and Dagger is going to spread that across your workers in your cluster or across your threads, whatever makes sense. You can go ahead and do operations like a map on it, and importantly in Dagger, it is an asynchronous, lazy system that runs work in the background. So you launch work, and you can launch more work based on that, and keep going and keep going. It's not going to block until you say, okay, now I finally need to materialize a result. Give me back something I can work with, like a Julia array. And so collect is kind of doing that here, but we also use base.fetch for a lot of our APIs to say, here's something that's still maybe computing that we don't yet have. Let's actually get that result. Let's finally materialize that, but lazy by default. So that previous example was distributing an existing array. You can also call a function to just allocate your random arrays directly on your workers. Obviously, that's more efficient if you can do that. So we have APIs for that. You can do rand, ones, zeros, whatever. You just basically add this block specifier as the first argument with your desired partitioning. So things like reductions and broadcasts and all the array stuff that you expect are within the purview of the D-array, and we plan to support all of these. Not everything is fully there, but we're getting there. Broadcast being a big one that does work today. So all of this just works fine, as you'd expect. Go ahead and build up your broadcast expressions, no problem. So yeah, I've been telling you that it's distributed. I've been telling you it's multi-threaded. Let's prove that. I'm not going to run the code today because we know how live demos go. But we can see, okay, let's map over an array and let's return the worker that we're actually running on. And here we can see that, and it's, kind of running off the side of the page, but we can see, yes, we were running our blocks of our greater virtual array, our D-array, are executing on different workers. And as I said, we can prove that we're using multi-threading as well. We do the same approach, just return the thread ID, and we see, yeah, we're running across all different threads. And that's across all of the workers. If worker 2, worker 3 has some number of threads, we're aware of that. We use them. So one really cool thing about the D-array that I wanted to highlight today, we have an amazing Google Summer of Code student, Felipe Tome, that we've been working with. And he has been doing amazing things with taking Dagger's D-array, revitalizing it, and adding MPI support. So I'm not going to run this demo, obviously, in a Jupyter kernel. That doesn't exactly work. But you can load the soon-to-be-merged Dagger MPI package and basically go ahead and use a very similar syntax to what you just saw to allocate arrays, but across MPI ranks. And then do the same operations on them. You don't have to worry now that you're using MPI. It's happening seamlessly in the background. The Dagger D-array is doing the MPI operations for you. And this is nice. People don't usually like to have to write MPI code if possible. And again, yeah, you can see all the regular operations will work. How am I on time? Okay. I'm going to just run through real quick. We have distributed table support. If you saw my talk this morning, you've already seen some of this. Just like the D-array, we split things into partitions. It allows us to distribute and do a lot of parallel processing. Let's just run through this. We're also here just showing, yes, we're using distributed computing and multi-threading. The key thing here that I said before, there's a single low-level primitive system that Dagger provides, a set of tasks and data primitives. This is what everything is built on. You can build new abstractions on top of this. Just use that same API, you get all the same features. And you have an awesome scheduler, which is aware of GPUs and all that, which is great. Some of this stuff is still in progress, but we do have distributed loops and transducers integrating with the Folds ecosystem. I've been working on trying to get all of this together. Work in progress. And then something recently is that I've been working on is better GPU kernel support. So, you want to be able to integrate with kernel abstractions and do distributed GPU kernel programming. I've just got a taste of what you can do here. Of course, all of this is going to be online, so you can try this out yourself. But suffice to say, we try to support all of the GPU backends we can. We need one API support, but that's on the to-do list. We provide all the primitives you need for determining whether you want your kernels executing sequentially or in parallel. And you can really, that's kind of what these examples here are showing, but you can check out the notebook afterwards to kind of see how all of this works. That's basically it. In summary, use Dagger and let me know if there's anything that's missing any abstractions or any backend support, and we can make that happen. Thank you very much.
We have time for 1 or 2 quick questions.
So maybe this is a general question. So in several talks, you always see, use MPI-JL. Now, in principle, we have a concept of a compute cluster in Julian. We have the cluster manager and we have an MPI backend. But obviously, people use MPI-JL directly for a reason, I guess. But is there a path forward to where we can really just rely on Julia's integrated sense of what a compute cluster is and automatically choose the right communication path instead of saying, now I need to do Julia clustering, now I need to do MPI-JL directly, and so on.
That's a great question. That is exactly what I'm trying to target with Dagger, and that's what I'm trying to prototype right now with the D-Array. Is you change one little thing, and you automatically get the benefits of whatever cluster system you're using. In the future, it should be possible to even remove that part, so you don't have to specify that. Just let some code automatically detect, hey, I'm under MPI, let me use MPI. So hopefully that answers your question.
My point in general, why is the Julia cluster system with the MPI backend good enough?
That's a complicated... Potentially, there are many complications there. We should probably take that offline.
Yeah. So I just want to add, there's an SC workshop called Alternative to MPI plus X. I don't know if they'll succeed, but the conversation's there.